Right, hello, welcome back from lunch. I hope everybody's well fed. A couple of housekeeping items, just a reminder that the buses are leaving here sharply at 6 o'clock for the dinner tonight, and it's also possibly worth noting that this facility gets locked at 5:30. So if you're going to go somewhere and come back, don't expect to collect your bags at 6 o'clock if you're leaving on the bus. Okay, the other thing is we have some spooks in the room. The guys from NCSC are here, and to make them slightly easier to identify, if they're here they can stand up. So we've got Steve Martin and his team, and if anybody wants to talk to them about TICSA and Part 3 particularly of the Act, they're quite keen to have chats and they make themselves available. Okay, so we'll get started. So first of all, we've got Walt from Hurricane Electric, and he's talking about peering and peering security.
I love it. Large font for us older guys. Anyway, I'm Walt from Hurricane Electric, and I'm really excited. This is my first time here in New Zealand. I'm going to share a little bit about peering security. Some of you may know, some of you may not know, so the obvious stuff I'll speed up because not all internet exchanges are built the same. So here we go. Who am I? Well, I've been doing this for a long time. I've been with Hurricane for the last 4 years. We're currently on 206 exchanges in the world. We're the most connected and best peer network globally. We're in 184 POPs around the world and 42 countries. Prior to that, I was with Amazon for 4 years, 2 weeks, and 1 day. Ask me later and I'll tell you why. My primary focus was all of APAC, and you can read the rest yourselves. Prior to that, was with Microsoft for 13 years and was responsible for North America, South America, and Europe. Good news is that over the last several years, Hurricane's quality of service and our rating in the transit world has gone up significantly. Here's our backbone. We don't have football stadiums named after us. Every single money we make, we reinvest in the network and grow as quickly as we can. Here's another graph representing all the exchanges we're on, and I have a healthy competition with my friend Tom Passata from Cloudflare, and unfortunately they're quite a bit farther behind us. So catch up, Tom. It's a friendly competition. He's like my brother. So what does security have to do with peering? It's a lot now. You know, we can't just go out there and slap an interface up there and expect everything to work correctly. So most of the time, in other companies I worked for, it was an afterthought. But here are some of the basics, and this should be pretty much a common hat for you. Trust me, about 4 more slides will get a little more interesting. Defend your network, logical port security, routing security, and best practices. Many of the IXs around the world do provide good examples, but you'll be surprised the further you go into third world countries and other locations, not all networks exchanges are built the same. Just don't throw a common or a default interface on there. Actually, show of hands, in New Zealand, does everyone have a pretty good lockdown security? I didn't turn it up, so I don't know. We're pretty well locked down here? Question mark? Lack of response means yes. All right, don't use ARP. ACLs and interfaces. The Seattle 6, which I'm a board member of, does a very good job, and we do extensive testing before a port is put into production. Your network is at risk if you don't take care of your housekeeping. Your IX port can be a source of DDoS. How many of us experienced that in the past? We have. You know, there's no embarrassment. It's all about getting better and helping the community get better. It's IXP's responsibility to make sure your subnet's not being broadcasted to the world. And so far, it looks like most of Oceanic is doing very well. Here's the problem, though, is that our IP address on a couple exchanges are being routed. And this is a problem. This is pretty much going to be a theme going on here. And you can see that the different offenders, which is surprising. This should not be happening. So we have contacted them. They're moving forward to get a fix. Here's a reflection of Oceania. The green is good, red means it's being advertised, which is bad. So, and I've already talked to Gavin at Megaport, And he says it promises it's being fixed, so that should be resolved in the next day or two, Gavin? All right, make sure the LANs are not being routed. bgp.he.net is a quick, easy way to fix and look. I'm trying to get that incorporated into the IX report that we provide as well, so that you can look at you get to see. There's also on bgp.he.net. There's a health of the JSON feeds to ensure the data is up to date. So let's help eliminate the risk. A good tool that not Hurricane, but the Seattle 6 uses bgpmon.net. It's free, it's easy, it gives you alerts. And this is what it looks like. It's fortuitous that yesterday there was a hijack of the subnet that the Seattle 6 is on. It gives you, this is what it looks like. Tells you who's bad, and we can immediately notify them and fix it. So there's no reason why anyone shouldn't be taking advantage of this free tool set. So why do we care? Again, my friend Tom at Cloudflare experienced a 120 gig attack back in March of 2013, and it could have been simply prevented if the subnet was not being advertised to the internet. So basic peering, you need to filter your peers. We filter our peers. Actually, how many people in the room actually filter their peers aggressively? All right, every hand should be up next year. China Telecom, this happened a couple weeks ago, a massive leak. Everyone picked it up and leaked it and propagated a leak except for us. This is an Iranian state telecom that leaked over 100 prefixes. This has real impact. So routing security, you had to filter the routes you receive and the routes that you advertise. Starting with the routes you receive, there are simple ways. So who does prefix counts? So at my previous employees, Microsoft and Amazon, we would only set prefix limits, right? ASPath, who does ASPath filtering? Nice. And what about prefix filtering? Nice. Our new tool that's I announced last year at NZNOG is we now are running routing.he.net. So anyone that peers with me would have to be a bilateral session. You could put your AS in there. And for this example, of course, I use my friend Tom from Cloudflare. So you can see at the beginning is that you can see the AS Cloudflare set. You can also see that we also check via PeeringDB that both sets are there. You can also, when you click down, you can see the different exchanges and locations, what we're doing. You can see, and also you can see the date that it was updated. I use October because this is when I did the slide last, so I'm lazy. But if you dive down even further, you can actually see which prefix filters we're doing using per session, because not everyone advertises consistently, and I wouldn't expect a CDN to always advertise the same thing everywhere. So we're going to look at our Singapore peering session with Cloudflare. As you can see that the F means filtered, right? And we're looking at this bottom route here. That means we see it, we're not installing it because we're doing a prefix filter. And it's clear we're not installing it because it belongs to China Mobile. So Cloudflare is not a transit provider for China Mobile as far as I know. So Tom, if you want to be a transit provider, let us know, we'll update that. Here's our filtering algorithm. So just take the time to click through it and you'll see how we're filtering. We're filtering 90% of our peers now. We rolled it out solely because we didn't want to cause an impact globally to all of our sessions. But as you've noticed in the press in the last 6 months to a year that we've not been up there saying Hurricane Electric leaked a route, right? Because we are strictly filtering all of our peers. Some examples, I'll let you read them. So please take the time and check your filters. If you think that something's not correct, go ahead and email my NOC, and we'll do our best to take care of it for you or explain to you why we're not installing it. Over our 90% of our filtered peers are being filtered. And some simple resources, and thanks to Tom of Cloudflare for helping and providing data for the talk. One thing that I would like to mention is that we do have an open peering policy at this time, but we prefer bilateral sessions. If you're not peering with me with a bilateral, you're saving roughly 1/3 of the routes that you could be. So if you'd like to peer with Hurricane, please drop me an email and I'll take care of it when I'm sitting in the back of the room. Any questions? Thank you.
Exactly 3 minutes before you said use BGPmon, I got an EOL and end of life notice for BGPmon by email.
No, I just checked on the website and they just got bought by
Cisco, I think.
DNS.
They say Cisco's terminating BGPmon in 2020, and yeah, you should sign up for the Cisco security product.
Interesting. Well,
Yeah.
let's. That's amazing because I just checked so amazingly that between the time I wrote the deck and now I got thrown underneath the bus.
It was at 1:33 or something. Yeah. Anyone else?
If not, I'll be here all week. So come bug me later. Or do you have a question?
Okay, thank you. Well.
Thanks.
Okay, so now we are entering the SDN part of the program. So I'm looking for VJ. Yep, we have VJ Silverman and Craig from UNSW and Craig from CSIRO, and they're talking about network functions using SDN white boxes.
Thank you, Richard, and thanks for having us here. So this talk is about SDN, white boxes. I know it's a topic that many of you might have heard a lot over in the last few years, and it's gone through a lot of hype and whatnot, and may have many definitions and the likes. So you may have very strong views on it, but let's go through it, and I request you to try to, let's start from scratch and try to see what we can do with SDN with an open mind and see if we come up with something useful or not. All right, so, right, do I need to point it at something? Forward should work, yeah. So before we dive deeper into it, who are we? So I'm an academic at the University of New South Wales. I got my PhD back at UCLA, and I also was supported by Bell Labs, who did a lot of research. I've now written 150 plus research papers. Who cares? I've also been a switch vendor. I worked in the industry in a startup in the Silicon Valley for about 3 years. I've written lots of protocols. I wrote all the layer 2 protocols, all the spanning tree, rapid spanning tree, forest, what have you. And I wrote a fair number of the layer 3 protocols, RIP, OSPF, helped with the integration of BGP and the likes. Frankly, I felt I learned a lot more in those 3 years in the startup than I did in my whole studies. But reflecting on, now that I'm back in academia, I think there are great opportunities to actually put the ideas that we get in research together with the practice that happens in the real world. So that's one of the reasons for me to be here. And my colleague Craig, he's also got a PhD from Macquarie University. It happens to be in mathematics, right? But for the last 15 to 20 years, he's actually been a network operator. He's worked at PowerTel. He's built a whole network across the continent of Australia. It was a research network, and he still operates it. So the point I'm trying to make is that we are very excited by innovation, by research, by academic work, but we really think the translation into the real world has not been spectacular. And there's fundamental differences in the ways academia and industry think. Academia likes to see depth. I've had so many practical papers rejected just because it wasn't deep enough or intellectually gratifying enough. So we added some math and submitted, and lo and behold, it got in. Academia likes to see optimal solutions, whereas industry often likes to see simple solutions that actually work. And the focus in academia is always innovation. I have to look really cool when I stand up and present some deep mathematics, so people say, wow, this is so fantastic. But they don't necessarily think about, is it operable? Is it something that can actually operate in the real world? So I guess both of us have seen both sides to some extent, so we'd like to take a fresh attack at this problem of how to bridge this gap. And maybe, just maybe, SDN provides at least a platform or a means to try to tackle the gap. I'm not going to get into definitions of SDN, and you may have your own, But to me, simply, it separates the hardware brawn from the software brain. So you can make your brain sit in the software in general purpose compute outside of the box supplied to you by a vendor, and you can let the hardware do what it does best. Keep it dumb, but keep it fast, right? So we think it's a great opportunity because you can do innovation at the velocity of software. But you can let the hardware, you don't want to sacrifice speed, you don't want to sacrifice data rates. You still want to be working at 10 gigs or 100 gigs or beyond. So you want to still have that hardware. So the opportunity is to try to bring them together. Use the flexibility of software and the innovation in software with the high speeds and scalability that you get in hardware. Of course, the challenge is now you have different providers. You have a hardware vendor and you have a software supplier. And then the whole ecosystem gets horrendously complex, as many of us are finding who are working in SDN. So about 5 to 6 years back, thanks to several people in this room, I don't know if Josh Bailey is here or not, and a whole bunch of people working at Wand and Rian's and the likes, we put together an NZSDN Alliance to try to build a bit of community around understanding how this ecosystem is, because it is getting quite complex. Now, SDN can do magical things, and I'm sure my next speaker, Brad, will be talking to you a lot about how to use SDN effectively to run and build and run your network. This talk is actually not about building or running a network using SDN at all. It's about a point solution, a solution that actually sits in one specific part of your network and does a particular job. Specifically, we are focusing on middle boxes, things that do certain network functions, such as classification, cybersecurity, and the likes. So in some sense, we're trying to hide the SDN bits completely under the hood, so that you really don't need to even know that it's actually an SDN-based solution. But the point is, it'll achieve a certain function, it'll do it cost-effectively, and hopefully in a smart and flexible manner. So let's have a look at that. Typical middle boxes that you might be using are for deep packet inspection, load balancing, firewalls, NATs, and the likes. The physical appliances tend to be fairly expensive, especially when you start scaling them. So you go from having a 10 gig appliance to a 100 gig appliance for cybersecurity or for DPI. They tend to get pretty expensive if you buy a physical appliance. Over the last few years, operators and the vendor community also has been investing a lot of effort in trying to virtualize those solutions, VNFs. The problem we have seen and heard from various entities is that it does get difficult to scale. So if you want a solution that originally was a hardware appliance, but now you're virtualizing it, and you want it to run at 10 gig or 100 gig or beyond, it can get quite complex to try to scale the solution up, because general purpose CPUs are not really optimized for network packet processing and operations. So we believe SDN can help. We can combine that really fast and dumb hardware, which, if you look in the market today, operates in the simple kind of abstract notion of a flow. You match on something to call it a flow, you take some action, and you have some counters with it. This very simple abstraction lets you take an action like I want to drop the packet, forward the packet, copy the packet, edit the packet, and so on. And there are multiple vendors out there who are selling these kind of white boxes. We work with a few. These boxes we are using, 400 gigabits per second box, supports large table entries, lets you do arbitrary stuff, and it can be controlled, or the table entries can be programmed from the outside. And we are starting to see the emergence of more programmable hardware platforms which are operating at 6.4 terabits per second. Specifically, from Barefoot Tofino is one example. And these are fairly cost effective. For $20,000 to $40,000, you can actually get a hardware switch which can do an arbitrary match in action, and in fact is even more programmable than that, at 400 to 6.4 terabits per second. So that's pretty good in terms of speed and scale. On the software side, you don't want to be processing all packets in software, but you can do smart stuff on the packets that you do want to work on. And you can apply, you can do deep inspection, you can do stateful operations, you can apply all kinds of machine learning, AI, and all that kind of stuff. And you can also scale out as and when you need more compute capacity. You can use DPDK to enhance it. It's flexible, it's agile. You can use all the development tools that you're fairly comfortable with. And you're no longer beholden to the vendor who supplied you with the hardware. And that's the most important bit. So how do you put the two together? Here's a simple kind of a general principle we try to follow, which is whenever possible, operate on flows. Because if you can isolate and operate on a flow, you don't need to be worried at the packet level anymore for that flow. And only when you can't operate on flows do you actually work on packets. Why would you want to work on flows? Because it is well known, and for most of the statements I make, I have put academic references, so we hope they're fairly backed up. We know that at least 3/4 of the network traffic is actually carried in long flows, the elephants, the heavy hitters, various such words are used. And those heavy hitters happen to be just about the top 5% of flows. So a vast majority of your network traffic is carried by a small number of flows. So if you can pull those flows apart and act on them as a flow, you don't need to work at the packet level anymore for literally 3/4 of your network traffic, right? So that's the very, very simple idea we start with, which is work on packets in the virtual space, namely on compute, and work on flows in the physical space, namely in the hardware, right? And we call this model SDN accelerated network functions. And the advantage is that your software doesn't need to deal with every packet. You only need to deal with, let's say, 1 in 4 packets. So you can actually make it a more scalable solution, and your hardware is dealing with the majority of the traffic, but only a small number of flows. So you don't need that many table entries in your hardware either. So put the best of the two together and find the right partition depending on the specific application that you're doing. So we'll see how this simple paradigm can be applied to several examples. And just to take a few, for example, if you're doing NAT or load balancing, often you know what to do pretty much in the first packet or the first few packets of that flow. And once you know what to do, and that's the software intelligence, you can then go and program a hardware to do that repetitively for all subsequent packets of that particular flow. So you can, in other words, offload that flow to the hardware. And today we'll be looking at 2 specific examples that we have actually built and deployed. One is for traffic classification. How do you get this mix of hardware and software right so you can classify flows easily, scalably, cost-effectively? And we'll also talk a bit about a firewall or a security appliance. OK, so first use case is around traffic classification. Why would you want to do that? Let's say you want to understand what is the breakdown of traffic, or the types of traffic that's going on your network. Let's just take a broadband network as an example. So in this figure, I've shown some of the data we have on the gray traffic. Firstly, this is a 24-hour pattern from midnight to midnight, so you can see the pattern of how it kind of dips at 3 to 4 a.m. and then peaks and peak hour at 6 to 9 p.m. Or thereabouts. The black is the download traffic, namely the long flows that are not streaming video. Streaming video is in green, and the gray represents the so-called mice flows, like web browsing. And so this kind of gives you a breakdown, visibility into what is actually happening on your network at different times of day. You can break it down even further, and you can look at the video by provider on the rightmost. So red is YouTube, purple is Netflix, and so on. And you can see that the pattern is not necessarily exactly the same on all days. And the plot in the middle, you'll see literally a vertical wall of downloads at a particular time on the network. And this was actually a Fortnite Season 4 release day. So that's when a lot of users on the network were actually downloading that game, which is multiple gigabytes. For those of you who are aware of Fortnite, you might recognize that. So getting this visibility into the mix of traffic can be quite important if you want to, for example, manage user experience, or you want to just understand how to provision your network. And over a 30-day period, just look at the variability on the traffic. This is data that we have collected over a 30-day period in an actual broadband network. And we focus only on the downloads, and you expand it out, you'll see a couple of spikes. Those are actually correspond to Fortnite releases again. So knowing these trends and patterns can be quite important from a provisioning and user experience point of view. Now, DPI has been done for many years, so what's new here? We actually don't do DPI, as in we actually don't look inside any packet at all. So it's a bad term for what we do. We actually do flow classification. So what we do is, once we know a flow is long, we offload it to hardware. And once it's in hardware, we track its counters and build a behavioral profile for it. So we have not looked into any packet at all, other than DNS. So we build a behavioral profile, and then we extract a set of attributes from it, run it through some machine learning classifiers, and are able to quantify with a 98% plus accuracy as to whether or not they're streaming video, whether or not what resolution they're running at, which provider they are from, and so on and so forth. So And of course, just to be able to visualize, we built a user interface where we can actually see the breakdown of the overall traffic and for the last hour, the last day, and so on. And we can actually get a list of all the long flows. That's all going into our DB, so we can always do a post-analysis on them. So this system has been running in our own campus network for upwards of 12 months. We have generated a lot of good insights, which we have shared with our own IT departments on what's happening on our campus and our dorms. And we have also put this actually in trials with certain telcos. So, in fact, it works so well that we have actually spun it off as a company, Canopus Networks, and we are giving this as a commercial offering. As I said, we are in trials. We're able to give insights into video consumption patterns, from real-time, hourly, daily, and also the large downloads. As I said, Fortnite was a particular pain point, has been a pain point with several providers in Australia and other places. And we are now starting to partner with some of the inline vendors. We extract the intelligence and the classification, and we feed the signals back to inline vendors in order for them if they want to manage the bandwidth and the user experience. So, of course, two things to note. One, it seems Australia seems to have much better and much cheaper network connectivity, especially on the broadband, compared to Australia. So I guess you guys are lucky here and don't necessarily need solutions like this. And the second aspect to bring up is that net neutrality can become an issue. So we are very well aware of that. In fact, we have written quite a bit about it. And it's something that we'll be talking again at the Symposium on SDN Research in a couple of months. So that's one of the use cases. And the second use case is around cybersecurity, for which I'll invite Craig to come and talk a bit about it before we wrap it up.
All right, so yeah, following directly on from Vijay, use case number 2, cybersecurity, and I think he alluded to the motivation earlier in the talk about cybersecurity appliances. Typically, the solutions are provided by appliances that are very expensive, particularly at high data rates. And we've found, talking to university networks and also within my organisation, CSIRO, that the actual network service from the provider can be significantly cheaper than the security solution. So that's an interesting problem that we thought we could look at this way of thinking to look at that one. They're also bundled, so you get your security appliance from your vendor, and it's probably quite a good solution. But there's very little you can do with it other than use their solution. You can't, if another software provider comes up with a better algorithm to do some detection or some remediation, you can't just swap it out very quickly. So you don't have that ability to modularly put in different algorithms. And also, the conversations we had with people that run enterprise networks, large enterprise networks, is that even though their security appliance is expensive and runs at a very high data rate, it only runs at the very high data rate when a lot of the features are turned off. Turn them on and the performance goes down. Why is that? Because often a lot of the security features are quite computationally intensive. So our goal was to build a platform called Nozzle, or to try and build a platform to augment these current solutions. Now, the name Nozzle comes from a couple of interesting things. Firstly, Vijay alluded to our long-term relationship with some people in New Zealand at WAND, and Josh Bailey, who some of you will know, and Faucet. So we built this on top of Faucet, and we were good users of Faucet, and we thought of another word that represents something like a tap. And also there's Oz in there, which is Australia, and there's NZ in there, so nozzle sounded like a good word, right? And it's a security solution, and the idea of a nozzle is you can turn it and it gets smaller and bigger. Anyway, you've always got to have a good name. So the idea with Nozzle was to leverage the white box SDN hardware and the commodity server class compute, right? And to do a security solution that's scalable so that you can swap in and out relatively easily, is very flexible, so you can use the best solution at the time, and if a new security threat emerges, you just transfer to that solution without having to forklift upgrade all the equipment, and is relatively low cost, right? Low cost is a relative concept. So relatively low cost compared to current appliance-based solutions. So it utilises, in an abstract sense, this idea of a set of workers that extract attributes, and I'll allude to what those are, and that's the SDN part. And then I think Vijay mentioned machine learning and artificial intelligence. Now that's the really That's the brainy sort of software-based intelligence part, which you can do in the server class compute. So why use SDN for cybersecurity? I think we've probably answered that question, but one comment I will make is, talking to a lot of people in the network community in forums like this, is there's a perception that software-defined networking is just another way to move packets around in routers and switches. But the ecosystem gives you the ability to do a lot more than that, which I think we've tried to explain. So when you bring in the scalable server class compute and a programmable control plane, and the astute amongst you will notice I've not said a programmable data plane there, but a control plane, you can extract flow attributes, right? And I'll allude to what they are. You can do complex data analytics, you can use machine learning and artificial intelligence, basically because you've got a lot of compute power there, right? That doesn't have to forward the packets. But then you use that intelligence to close the loop and control the packets based on what you can compute. So it's a very good, or potentially a very good fit for cybersecurity. So a very high level, and I stress very high level diagram of what a nozzle platform would look like, and I will use one of Vijay's favourite analogies of a medical analogy. A high-speed data plane, you copy off some packets to the server class compute that is bad or is sick or is ill, right? So when you go into a hospital and you're sick, you need a diagnosis. The detection, or the scalable work, is diagnosed by sending you to radiology or get a blood test or something like that, right? So that extracts the attributes, but the guy who takes the X-ray doesn't diagnose the problem, right? You then send the X-rays and the blood test results to the specialist, the cancer specialist or the orthopedic surgeon or whatever, and he or she looks at the results, makes the diagnosis, does the really intelligent sort of stuff that they've been well trained for, makes a decision and prescribes a solution or a medicine, and that's communicated back to the people that then treat you as you leave the hospital or the surgery or whatever it is, and that's an API back to an SDN controller. And in our case, the SDN controller is Faucet, which Brad will talk about in the next talk. But at a very high level, that's conceptually how it works. High-speed data plane at the bottom that just forwards the packets at, 10, 40, 100 gig or whatever, but all the intelligent stuff is done in the server class compute. So in the nozzle platform that we built, just a sort of a list of what technologies are involved. An SDN switch, an OpenFlow 1.3 switch with multi-tables, 100 gig interfaces, plenty of them around, right? The particular one we used was from Noviflow. And server class compute, so generic server class compute, put some 10 gig Intel X710 cards or something that supports DPDK, so you can do fast I/O. That's all the hardware you need, right? A lot of software though. So a RIU SDN application controller, which in our case was Faucet, a flow extraction module written in Go, some sort of messaging system to pass messages between them. We use Google protocol buffers for that and NATs, some machine learning algorithms, which you can write in high-level programming languages like Python and Go, some time series databases, open source stuff, and a visualization and operator UI, which I'll give just a few screenshots of what that looks like. This is the front end to the system, and it's running in a lab network. But the point I want to make here is that there's a split between hardware and software. And in this particular screen capture, it shows that the total load going through the system is 20 megabits per second, 11 megabits is software. So there's a 50% inspection ratio. The point is that some stuff is offloaded to hardware, some stuff is being looked at in the software. And there's a bunch of flows that are pushed into the hardware. And if like Vijay said, as the network capacity increases or there's more traffic on there, can be covered in a few flows, a small number of flows, push it up to like 8.5 gig or whatever, and there's only 10 megabits going through the software, so the inspection ratio goes down to 0.1%. So only a very small number of packets are actually looked at by the software. The ability to put static ACLs and things like that directly into the hardware, we put that in there. You can look at the flows that are in the hardware. So what do we mean by attributes, and what attributes might be interesting for security analysis? So DNS attributes, things like query and response volume, whether they're solicited or unsolicited packets, resource records, time to live, the length of the subdomain field, host level attributes. Attributes are all distinguishing features of flows in the network, right? We talked about long flows. A long flow attribute is just the volume, the data volume in a flow. gaps between the flows, between the packets, and a whole bunch of, I mean, there's no end. You can, especially in the security world, there's tons of attributes that you can examine, do computation on, throw away if they're not interesting, whatever. But when you don't have to worry about forwarding the packets while you're doing that computation, it makes it a lot easier. So the one we focused on initially was DNS. Why DNS? Well, because it comprises a very small volume of the traffic. In most enterprise networks, it's allowed through firewalls. Certainly, UNSW and CSIRO, all port 53 traffic is allowed, so it was relatively easy to capture. It's a very small volume of packets, but contains an awful lot of information, and is not too hard to do analysis on. So we thought it was a good one to try first. The DNS worker in Nozzle is just an SDN flow rule. Match on port 53, copy it out of port, bung it into a server, write some Go routines to do some analysis on it, and then publish aggregate records to the NATs every second. And bingo, you can start making a lot of decisions about what's going on in the network. So we ran this on UNSW's DNS traffic over a period of time, and the 10 gig border connection at UNSW runs at, I don't know what, 7 or 8 gig per second. It's almost full, right? The DNS traffic's only 10 megabits a second, right? So it's a very small percentage. So what we did was extracted 4 attributes per host: the outbound and inbound queries, the number of external servers, the number of internal clients, and the fraction of active time, and built a simple clustering machine learning system. And we were able to identify 40 name servers, 14 resolvers, and 368 public servers on campus, all done automatically. Took that information to the IT department around network, and they said, yeah, we can verify most of that, and actually there's a few there that we didn't know about, so thanks for that information, that's very good. So the result was that it's fully automated, so every day it produces these results. So again, because it's done off data path, right? And there's a reference to a paper that's been outlining all those results. We discovered evidence of quite a lot of attack vectors in just analysing DNS. Scans, recursive resolvers used for reflection attacks. In fact, one of them was when we asked the IT department, do you know about this one? And they said, oh yeah, that's the bookshop that run their own DNS server but still uses our link, and it was being used for a reflection attack. The other one we looked at was DNS exfiltration. Don't really have time to go into that in great detail, but essentially the DNS channel can be used by malware to exfiltrate information outside the organisation. There's been lots of published results of that, or reports of that, exfiltrating credit cards and the like. So we built an ML algorithm that can detect by looking at the following type of attributes, like the length of the domain, the entropy in the domain field, how many numbers are in it, how many capital letters, how many dots, that kind of thing. All of these kind of things are very, very well suited to using machine learning and artificial intelligence algorithms. We were able to do DNS filtration between CSIRO's network and UNSW's network, and the corporate firewalls didn't pick it up, and our tool picked it up. So the enterprise network system probably, don't look for it, but we were able to actually run a credit card exfiltration where we just generated a whole bunch of card numbers and exfiltrated them using DNS, and it was relatively easy to do, and our tool picked it up in real time. So there's another paper there as well. Back to the GUI of the Nozzle system, that's the DNS mapping part, which every day just produces the statistics about how many DNS servers are on the network, then categorises the servers as being authoritative or caching servers. That's the kind of thing it does, right? And the last one I'll show is the DNS packet stream. So that's the one that does the exfiltration, and you probably can't see, but there's a little anomaly score there, and it calculates a number between 0 and 1, and if it's above a certain threshold, it's something that potentially looks like an exfiltration. And the beauty is, because you then have the 5 tuple of the flow, so you know the flow, so you can then either isolate the flow, drop the flow, or you can send the flow for further analysis by pushing a rule back via a software API into the hardware to capture just that flow, just that one that you're interested in, or to drop it or something like that. So I think it illustrates the point that the software-hardware split is very, very powerful. So I will finish there and let Vijay conclude.
Thanks a lot, Craig. So I mean, we're not saying that the existing firewalls are not able to capture the exfiltration that we did and we demonstrated. I did talk to the IT person, and they said it's possible they've turned the feature off because otherwise there's a performance impact. But if that is reality, that's definitely a problem worth tackling. It's not just whether the box is ticked on the appliance, whether it supports the feature or not. In reality, is it usable or not? And often it turns out, in reality, turning it on has a performance impact, so a lot of operators tend to turn off things. But one shouldn't have to do that, really. I mean, one should not compromise on features just because it's affecting your performance. And that's kind of the motto behind Nozzle is we want to build both a scalable system that scales gracefully, but at the same time doesn't compromise in terms of the capabilities, which is why you can scale up the workers and the filtering by using this combination of hardware and software. So we are hungry for trials, right? The only way this system can be improved and got to the stage where it becomes a true commercial offering to replace the relatively more expensive bundle solutions that you get on the market is if it goes into trials and in the process gets better. So there are many models of how this could potentially be trialed. We are talking with our own university because they are looking to upgrade the link this year. And once the links get faster, the appliances get more expensive. So we are definitely talking within our own organization. And a low-risk model could just be to take a tap and send it to Nozzle in addition to your existing appliance, firewall appliance, and see if the analytics that comes out of Nozzle matches or exceeds your current appliance. And who knows, maybe there is even some intelligence that comes out of Nozzle which is then possible to use to go and either manual or automatically update the firewall to block that threat. The other model, if one wants to be really adventurous, is to actually insert Nozzle as the solution that sits between the enterprise and the broader network, with a potential bypass in place so that if it needs to be taken offline or it needs to be upgraded or something, that's possible. There could be models in between where we also have a version where we can identify safe traffic using the classification platform that I talked about earlier, and using that to know with fairly high certainty that this is a YouTube or a Netflix stream and is therefore safe, and you can therefore bypass your existing appliance. So you don't put unnecessary load on your existing appliance to inspect packets that you're fairly confident are safe, right? So there are many modes where this could be tried. So I'll conclude by saying that we believe that accelerating network functions by using SDN, namely finding that right mix of hardware and software, is a very promising approach. It has a strong value proposition. Cost can be a lot lower because you're using commodity hardware. You can get many vendors who can provide you with the right speeds and port densities. We believe it's a very modular and elastic system, so you can scale in performance. And most importantly, we have unbundled it. So you're not beholden to one vendor for all your security. It's like saying you have to go to the same doctor no matter what problem you have. If you have cancer, you got to go to the same doctor as you go to for a headache. Like, it shouldn't be the case. You should be allowed to choose from a whole range of diagnosis techniques out there, provided you extract the attributes at high speed and you're able to present that reports and get a second, third, fourth opinion if you so desire. Right? So we are looking for operators with the curiosity and the appetite, and we acknowledge there is obviously some risk here because it's not a certified solution that has, all the certifications needed to be deployed, but we are happy to go through those hoops, provided we have the right support. We're not going to do everything and go to at the end of 5 years, come out with a product that we'll put in front of you because we can't sustain for that long without that support early on. So we are happy to co-develop and test innovative solutions, get new insights, improve it. So we really, really would like to talk to you today to see if you might be interested in a trial. I'll just finish by saying there have been many sponsors for the various bits of SDN work we've been doing, and these are not the only ones. There have been many more streams going on for the past few years. Of course, the Australian Research Council, Google particularly would like to thank. They've supported us on multiple occasions. Some of the carriers, Optus, Telstra, Arnet, vendors, Cisco, HP, Noviflow in particular, Australian Defence, and the Open Networking Foundation have supported a lot of our work over the past 5 years. Thank you very much.
Are there any questions for Vijay or Craig?
I saw you using Nats, which is basically written in Go, and then what's the preference compared to Kafka and things like that, or it's just because you're using Go anyway, I guess.
Yeah, the engineer we use for that, Himal, he did an analysis between NATS and what was the one before that, Craig? No, not Kafka. It was. Was it Redis? Maybe I'm not sure. Redis, yeah. Yeah. Look, yeah, that's which flavor you personally prefer based on language and support and all that kind of stuff. So he decided NATS, and he's the engineer. I said, fine, that sounds good to me. So.
Anybody else?
Well, I'm available all day, and I would really love to have a chat with anybody who's interested in this. So.
Okay, so thank you very much for your day, Craig. So, those of you who've been to the last couple of NZNOGs will possibly remember that the network here has been run by a small SDN controller called Faucet. And only 2 years ago, it was a pretty primitive thing. So Brad is going to come up and talk to us about what happened next.
Well, that was very dramatic, wasn't it? And thank you to Craig and Vijay for setting the stage for this talk. We'll build a little bit on what they were talking about. So, yeah, as Richard said, I've given talks on Faucet the last couple of years at NZNOG, but this is the biggest one yet, and presumably that means there's new people in the room that haven't been before. So I'll just go over a quick recap of what Faucet is. So it's an SDN controller that uses OpenFlow as its API. It's primarily programmed by engineers here in New Zealand, though we have another 40 contributors from around the world as well who have helped us out a lot. We call it a lightweight SDN controller, and the reason why we call it that is it doesn't need a big cluster of machines to run it on. It'll run on anything right down to a Raspberry Pi all the way up to a regular commodity server. We call it production quality because it's deployed in a bunch of places now, and the rest of this talk will be about a particularly large deployment we did last year. And we spent a lot of time testing it because the last thing you want is a bug or regression to sneak into your SDN controller, and when you upgrade it one day, your packets go away. So we have a comprehensive unit test and integration test suite. So our unit tests test over 90% of the code we've written, and it's lightweight. There's only 10,000 lines of Python here that we're talking about. Our integration test suite lets us test against software and physical devices. So we qualify it against devices from about 4 or 5 different vendors at the moment to make sure that our code works on their devices. The multi-vendor aspect, so we program every device with standards compliant OpenFlow. We don't use any vendor extensions or modifications. That's key so that we don't have to have a hardware abstraction layer or various drivers throughout our code to mean that different devices get programmed in different ways and bugs and stuff can sneak in that way. Faucet itself implements all your regular L2 and L3 features. We call it an enterprise environment controller, so it sort of replicates anything you want to do on an enterprise campus. And if you don't want to dig in and write some Python to modify it, we've got a policy engine that lets you override the default behavior of Faucet and provide your own with a couple of easy lines of YAML. Just very quick, brief OpenFlow thing. So Vijay covered this pretty good, but yeah, the idea is we're moving the control plane functionality from a small embedded CPU on each device, and we're putting that in a bunch of regular server infrastructure, commodity hardware. This lets us sort of modify functionality, implement new features, that kind of thing. And the way OpenFlow works is you get these match action rules. So a match is on a bunch of header values in your IP headers, TCP headers, whatever, and then you can have an action associated with that flow rule. And so an action might be drop, it might be change parts of the packet, it might be add VLAN IDs, various other tunnel IDs and that kind of thing, or you can output to a port. So these rules live in tables, and the way you get scale and smart logic is use multiple tables, and that gives you branching, so you can make decisions based on parts of the packet. And that's how you can reduce your flow count and do smarter things. So this is a basic architecture overview of Faucet. So we've actually split the thing in two controllers. So Gauge is our read-only controller. It handles all the monitoring. So it polls all your switches for port stats, drop counts, that kind of thing. And that pushes to a series of different database backends, Prometheus, Influx, or flat files. And you can use things like Grafana to watch what's happening. And then Faucet itself is the read-write controller that actually implements the network behavior. It ingests a YAML config file that describes the network and converts these to OpenFlow rules and pushes it down to the switch. Faucet itself knows how to talk BGP, so you can get routes into it. It puts a fib for v4 and v6 in the device, so it can do all the routing at high speed on the actual ASIC. And then you can use an external system which you can point events at, so that's how you can kind of hook into Faucet. And we send a bunch of instrumentation data to Prometheus so that you can actually see what the Faucet controller is doing. So here's a sample config file. It's pretty simple. Everything's YAML. It's a bit simpler than all those crazy XML things we saw this morning and Yang. It's also multi-vendor, so you can use that same exact config file to push to 6 different vendors today, and it'll be implement the exact same network behavior on all of them. So in this example config, we have a list of VLANs and a list of DPs. DPs are data paths. They're what you'd regularly call a switch or a router. So in this example, we've got a single VLAN. You can have a description there, and then that goes into Prometheus, so you can pull that out later. Faucet can have an IP address on your network, virtual IP. That's so you can use it as a router as your next hop. And then in this example, we've got a single switch. It's got data path identifier of 0x1, so it's the first switch. It's an OpenV switch, which is a software switch. And then it's got 2 ports all in the same VLAN. Now, important thing to note about Faucet is it's idempotent, and that's how we get high availability. So instead of having this big cluster of controllers that have to synchronize their state somehow, we just make sure that if multiple controllers get the exact same config, then they'll program each device the same way. Then you just point each device at independent faucets, and then that's how you get HA. So now onto the fun bit, and what I spent a large chunk of last year working on. So there's this conference in the US called SC. It happens every year, and it's a big HPC conference. Last year it was in Dallas in November, and it was the 30th anniversary of the conference. And as part of this conference, every year they build this thing called SciNet, which is a massive, huge network. It's, I think, the world's largest temporary network. It exists in production for a week, and I'll go into the sort of scale of the network. And what it does is it powers all the wireless, there's a trade component, and it powers all the trade booths. It does internet in all the workshop rooms and seminar rooms. So the SC conference gets about 14,000 people through it. And last year we deployed Faucet on this network, and I'll go a little bit more into that. Okay, so these are the stats from SciNet last year. Here's my colleague Lance, who was our, I call him the chief diagram officer. So that network he's standing in front of, he hand did that entire diagram. So every box on there is either a switch or a router or some kind of optical gear. Each line is either a 10 gig, 100 gig, or 400 gig link. And this year, or rather last year, we hit 4.02 terabits per second on the internet connection. The rest of the internet, the rest of the network had much more capacity than that, but that's how much internet we brought into the show floor. Vendors were kind enough to let us play with $52 million worth of equipment that weighed a lot. And turns out when you have this much gear and fiber cables and craziness, you need about 225 people to run this thing. And we were all volunteers. So let's take a step back. How did a bunch of Kiwis get involved in deploying SDN on this huge network? Well, we basically sent them an email and asked if they'd be interested, and it turns out they were. So we were able to help them with a couple of pain points that they were coming up against in scaling their network, and we're able to reap the benefit of deploying on this prestigious conference network. So once our proposal was accepted, we sort of began to do some work. And this was separated into a few different phases. The first one obviously was planning, like working out what are we going to deploy, what does it look like. So this involved many, many months of video conferences to the team that run the conference, who was split between USA and Europe. Our particular team that was planning our deployment was split across Hamilton, Wellington, Berkeley, Champaign, and Dallas, and they're a team of about 10 of us. And kind of the first thing you do is you generate some requirements, you generate a scope. So we decided early on that we'd do a parallel deployment so that they wouldn't step on our toes and we wouldn't step on their toes, because we didn't really know how to integrate into this huge big ecosystem that they've been growing over the last few decades. So that was just the easiest way to do things. And then we'd do some simple BGP pairing between our side of the network and their side of the network so that we could route between each other. And then we'd provide a percentage of the booths on the show floor with internet access. So it ended up being about 25% of the network was run on Faucet. So booths can order a connection for this conference at 1G, 10G, or 100 gig. Yes, that's right. On your little rectangular stand at the conference, you could get a 100 gigabit internet connection. It's pretty good. And then they have this Django web app that tracks all the connection information, all the subnet assignments, and that kind of thing. And we needed to write a little bit of code to integrate with that so we could provision all the circuits. So we sort of came up with this mock design to start off with. It was very basic. And at this stage, we had no equipment. We had no real idea of what we needed to do. But this was as things were starting to form in our minds. So this thing's been running a long time, and they've got a couple of terms that you need to know what they mean, so the rest of the talk makes sense. So they call their core layer the NOC. So we all know NOC is the Network Operations Center. They also call that the devices in the NOC, because that's where they're physically staged. And so in the NOC is where all the big routers, where the internet connection comes in. And then the NOC feeds out to distributed NOCs, DNOCs, which are placed all around the massive show floor. And that's where the booths pick up their internet connections in the DNOC. So in this diagram, we proposed we'd do 200 gig lags to both their core routers, and then we'd go into a Faucet NOC device. So that was a router that we put in the NOC. And then those DCIs are just data center interconnects. They're optical transport gear, because you don't want to run hundreds of pairs of fiber between all the DNOCs that are forever away. So you do some optical transport, and then you can just run one fiber or a couple of strands. And then we'd need to go into each of the DNOCs, and then that would feed out to the booths. So we did this project kind of backwards. We designed the network, and then we had to go find some hardware. You'd think this would be hard, but big thanks to Allied Telesys, Cisco, and Novaflow, who after a few phone calls and emails were very, very keen to help and supply some hardware. So they each supplied 2 OpenFlow devices each that were qualified against Faucet. And as part of our proposal, we said we'd build the network in a test lab first to show it all working, and then we'd ship that eventually off to Texas to run the conference. So we coordinated with all these vendors to get a list of everything that we needed from them, and then we submitted that all to the conference so they could insure it all, because it turns out this stuff isn't cheap. And we didn't want to be on the hook for if we lost anything. So we sent this all to our lab in Berkeley, which we were going to build it all in. And this actually takes a couple of months. It isn't as easy to get that much hardware for free, turn up in a place in America. So while we wait, we can do some things. We're not completely blocking. So now that we knew what devices we were going to use, we could actually do a bit of a network design. So this is what we ended up rolling out. So there were 5 different iterations of this network with different devices in different places, but this is what we settled on. That big network conference diagram that you saw before, that went through 22 different iterations before it ended up at the final one. So this whole thing is in flux for about 4 months of people making all these different decisions and putting gear all over the place. So it's quite hard to keep track of. But basically what we did is in the middle of the network, we put a router. It was a Novaflow 32-port 100 gig switch with a barefoot Tofino switch. And this switch runs P4, and I'll talk a little bit about P4 in a second. And then you run a 10 gig network function virtualization link out to a Linux box, which is running Faucet. And that was so that we didn't have to implement any protocols on the switch, we could do that all in software on Linux. And then we kind of ran a bunch of 100 gig links through the DCIs into various vendor models, which all had various different port counts at 1G, 10G, 25G, 40G, and 100G. But we weren't interested in the hundreds, tens, and ones, and we came out with 75 hundreds, 146 tens, and 48 ones. So that meant at full capacity we could have done 9 terabits per second of OpenFlow. And I'd like to hear from anyone else who's built a similar sized SDN network. So we decided, so in Faucet we would do all your basic VLAN and L2 learning stuff. We'd give out V6 router advertisements from there. That's where we do the V6 assignments. We did inter-VLAN routing between all the VLANs. So each booth is in its own VLAN and subnet. So what they do as part of this conference is not only are the booths getting kind of internet connections, but they also want to talk to each other's booths to show off their demos. At the end of the day, it's an HPC conference where everyone's trying to sell the latest and greatest in HPC. So we had a bunch of data transfer nodes and storage nodes on our network. They wanted to do some demos to each other. You have to make sure you can cross-connect all the booths at 100G or more so that their demos work. And then we did a bunch of basic L2 security policy in Faucet, and that was doing like V6 router, guard, and DHCP snooping, that kind of thing, and you can just push that down with OpenFlow. We use ISU DHCP server and Bird for BGP on our Linux box to handle those protocols. So I mentioned that router in the middle of our network was a P4 switch, but Faucet's only an OpenFlow controller, so how did that kind of work? Well, this is how P4 works. So you as the user supply a program in a C-like language that describes how all the packets you want to move around look and what kind of matches and actions you want. And then your vendor gives you a P4 architecture model, which describes what the switch is able to do. They also give you a compiler, which can combine those two into a program, and also an API for your control plane. The switch loads the firmware from the compiler, and your control plane runs this runtime API. But it turns out what you can do is you can just write OpenFlow as a P4 application, and this compiles fine under the P4 compiler that Bearput supplies, and this runs straight on their ASIC. So effectively, it lets you use OpenFlow as a runtime API for P4. So we didn't actually have to change a single line in Faucet to make that device work, because Noviflow were kind enough to write all this for us. And I believe they sell that now. So we also did a little bit of development. So to ensure success, we identified all the features and protocols we needed, and we wrote integration tests to make sure that kind of worked. And it did, which was good. And then we kind of built a scale model at Wand. So one of the nice things about SDN and OpenFlow is, so I didn't have a single device that was going on the network, but I have ones that look like it. So I sort of plugged those in and made a 1 gig scale model and threw a bunch of traffic at it. And then the theory is if you can make it work on there, you can just take the configs over, run it on a different box, and point at the new hardware. It should work all exactly the same, but just at different port speeds. And then I started to work a bit on the automation. So automation is great for networks. So automation lets you define a set of tasks once, and then at no cost you can repeat that over and over again. This is perfect for network service definitions. And our deployment heavily used Ansible to deploy everything. So I mentioned before they have this Django web app that is kind of the source of truth for the network. And they go maybe a little bit more overboard than most. So they track every single patch panel, pair of fiber, fiber runs, fiber spools. Everything is in this database. And so you can look up exactly where anything is. Everything has a label on it. And you can find where any cable is at any time. And this can be useful for debugging your network, because you can easily spot when something's wrong or when you're getting the wrong circuit turning up, which is quite useful. And then I wrote a little tiny Python script that just basically scraped their customer database using all the Django models and produced a YAML file, which could then sit in my Ansible as sort of like a basic data structure. And then in Ansible, I just took that YAML file that defined all the connections on the network, all the information, and I used Ginger 2 templates to generate Faucet config and various other things. And so what you end up having is So there's about 300 lines of the sort of YAML file that define the network, and then you put it into 180 lines of Ansible, 260 lines of Ginger, and then you end up with this blowout of 1,200 lines of config. Now, if I had to write all those 1,200 lines myself, it would have taken me a while, and then someone would have said, oh, we changed the network, and then I'd have to go redo it all. But this way, you can easily automate that and reduce the impact when things change. So I kind of wrote that all and put up on GitHub as a bit of fun. So for people interested in large faucet networks, there's a URL there with all the generated configs, and I've sanitized IP addresses and other various things. And then my Ansible code, if you're interested in some hacky Ginger 2 and basic Ansible, that's all up there as well. Hey, everything got delivered, and everyone turned up in one piece, which was great. And a shout out to our friends at Allied Telesys, who actually load up all the gear they're providing in a car in San Jose, drove it all the way down to Berkeley, hand installed it, and then asked, oh, what else do we do? And we said, no, you've done more than we were expecting. So that was nice. And then, of course, we enter the testing phase. So I'd already sort of got the Ansible all sort of worked out. So you do a generate of that, you load it up, and you see if the switches boot. And then the idea is to throw a lot of traffic at it and sort of simulate what the network's going to look like. So I've found network namespaces are fantastic for this. They're an incredibly lightweight thing to do on a Linux box. You can easily spin up thousands of these on a single machine. And I just basically used a network namespace to represent a fake booth. In the end, I think I ran out of IPs before I ran out of the ability to spin up more of those. And I wrote some dodgy bash scripts that let me I had an onall.sh, which let me run a command on all the network namespaces, and they had this ping all thing that knew how to ping everything, and so you just run that on a loop, and then it reports every time there's a connectivity failure, and that lets you check that your L2 is working. I did a random iperf.sh that you run it, it finds a random pair of hosts, spins up an iperf server on one, a client on the other, and you make sure it can go full speed. Now, I only had 10G boxes to play with during testing, so I could confirm it all worked at 10G, but I had no idea about 100G. I kind of just trusted the vendors knew how to make ASICs, and turns out they did. Everything worked at 100G as well. So we did our sort of testing in Berkeley, made sure everything kind of worked, and then we shipped it all off to the conference venue in Dallas. And then we proceeded to hop on a plane and go chase it and see who turned up first. So this whole network's built in kind of silos by different teams working on different projects all around America, and this year the USA, this year New Zealand as well. Actually, quite a bit of stuff happens in Europe as well. So they do this thing called staging, which is a couple of weeks before the conference. They kind of have this room off to the side from where the show floor is, and they kind of build the network for the first time, and they see how it works together. This is where all the first kind of interop testing and diagnosing happens. So it's a little bit of a tense time because sometimes things don't work right, or sometimes the equipment doesn't turn up on time, that kind of thing. But I'm happy to report, the Faucet thing with all our testing came up first time. And so this is the staging team who got in and did all the setup. So we've got vendor reps and Faucet reps here. And you'll see behind them this mess, and that mess is the network. And it gets cleaned up before we go put it on show. So this is kind of the show setup, and this is why it gets staged away from here. So all while we're building the network, they're laying cables under the ground, fiber and power. They're putting banners up. They're building the booths, all the swag stuff. And so you kind of let them do their thing for a bit. And by the way, that's just half of the convention center. You go around the corner and there's another whole half. It was quite large. Come on. And so with all this heavy equipment, and because it all gets staged around the place, you actually install it via forklift. So it's the first time I've ever literally used a forklift to load my network. But and this is a little bit of a stressful time as well, but turns out forklift drivers are pretty good and they can put things in the right spot. And then what you kind of do is they have this kind of final date when all the connections have to be ordered by, and when they've sorted out their database and it all is consistent. And that's when we decided to do our automation trigger. So you hit enter on a laptop and it pushes out to the whole network. And when that's all said and done, you kind of got to wait for these booths to be built, because they're all built by contractors, and it takes a little while. And a lot of them are only built like the day before or the night before the conference begins. And so we kind of just waited around and for them to get built so that we could test that everything worked. And oh yeah, so this is what a DNOG that is the right slide. This is what a DNOG actually looks like. So it's a little sort of fenced off area out on the show floor, so there's booths around it. And inside it is a rack. And so at the top, we've got the regular switch, which was the regular SINET network. And the switch below was Faucet. And so they put fibers on either or, depending on which circuits we got allocated. And at the bottom is that optical transport layer, or the DCI. And then this is what the NOC looks like. So behind here is where all the operators sit, all 225 of them. And then that is the core of the network, all behind Perspex, so people can go and stare at the blinky lights and take their photos. And a lot of advertising and sort of displays around there. And so we kind of wanted to see this thing work at 100G to see if our months of work sort of paid off. So what do you do at a conference like this? Well, you go shoulder tap some people and ask who's got some 100G. And I was asking jokingly, hey, who's got 100G in their laptop? And someone said, oh, I don't have 100G on my laptop, but I've got these 2 little Linux boxes that are about this big with handles on the top that you can walk around the show floor with. I was like, oh, that sounds pretty good. Can I have 2 of those? And like, yeah, sure. So I went and plugged those into 2 different DNOCs to be 2 pretend booths, and we spun up iPerf, and you can see the little spike there. We got to 100G, so we're pretty happy. Now that was meant to be a continuous iPerf, but you'll notice there's a couple of gaps in there. Turns out the machine wasn't properly configured or something, and iPerf would keep crashing. So we could maintain better than iPerf was doing on that machine. So we're pretty happy about that. And then surprisingly, like showtime's probably the least stressful part of the network, because everything kind of works and everyone's pretty happy, and you're just kind of watching your ticket queue to see if there's any problems being reported by booths. And then we built a significant amount of monitoring for the network, so various live dashboards and alerting systems in Prometheus. I'm happy to report we didn't have a single page or any crazy issues. Most of the issues were things you'd probably expect from a network of this scale. So there were a lot of deploying light meters and working out where fiber strands were broken because someone had driven a car over or something. A lot of splicing, a lot of rolling optics because they'd been plugged in the wrong way. A lot of people bought multi-mode optics for their booths when the whole network was meant to be single mode. Turns out that doesn't kind of work. And there's a bunch of basic stuff like that. The people in the booths at the end of the day aren't networking people. They're just told to bring a switch and plug in. And at the end, so you spend 7 months planning this thing, 3 months testing it, 3 weeks setting it up, and you tear it all down in one day. And that last final day is just utter chaos, but it all gets done and everything goes back to where it came from. So what was kind of the things we learned from this deployment? So we learned it's really great to automate kind of like the basic 90% things you do. So if you got 90% of your customers look the same, if you can automate that, then you can spend your time looking after the more interesting 10%. So most of the booths, they just want an internet connection. They just want to get through things at the end of the day, and they're pretty simple to set up. There's a bunch of universities that turn up that want multiple VLANs and fiber pairs all the way to different continents, and that's the more challenging things to deploy. And by using something like Faucet to do the bulk of the use cases, then you can spend more time sort of hand configuring the more interesting things. Faucet effectively allowed us to ignore the underlying equipment. Anything could have turned up from the vendors at any time, and we could have added it to the network, which was quite useful. And we proved that 10,000 lines of Python written here in New Zealand could handle many terabits per second. So there's a picture of the Faucet team in front of our network, a couple of those people around here at the conference. And then I think I've got some time for questions. So that's all 225 of us. Happy that everything was over and worked well.
Questions for Brad?
Can I do it again? What was the question? Would I do it again? That's more a question for my boss than myself. It is obviously a lot of time, but yeah, it was enjoyable, that's for sure.
G'day, Joel from Red Hat. How do you solve the service coordination problem between routed BGP domains?
How do I solve the...
So you've got your VLANs coming down to your top of rack equipment that you're programming via OpenFlow or whatever your common denominator is from your controller. From there, when you're doing your routing between the top of racks, like you've got some sort of service coordination model that you have to advertise the routes between your different instances. Say, in the typical scenario, you'd be going between DCs. How do you solve that problem with Faucet?
Okay, I think I understand it. We just went really simple, and we just brought all the equipment up to the core router, and that did all the IVR. So it wasn't actually done on the access network. But for like 6 switches, I don't think you really need to do that. And the core router was massively over-provisioned for that reason.
So you talked about how during the conference you only had the minor BAU issues. Did you have any issues related to Faucet itself? Any misconfigured ports, or did that all work 100%?
Okay, I had one minor cock-up with my automation. So, automation lets you do, you do one thing and it does it lots of times. So if you make one mistake, it does it lots of times as well. So luckily, my monitoring caught my mistake. So in my automation, I provisioned one of the switches slightly wrong, and the monitoring told me straight away I'd done it, and I just fixed my bug and pushed it out. That happened days before the conference began. There were no issues during the conference.
What did the controller architecture look like? Did you have 2, 4 controllers? Did you have to load balance?
So we had 2 controllers. We were going to shard it a little bit more, but turned out the load was fine. So that Faucet controller hardware, we just randomly found it on the floor of one of the test labs we were using. So we possibly should have done a little bit better in procuring our hardware, but everything's UPS'd and powered fine. So we thought we'd get away with it, and it turns out we did. Of course, the network's in production for a week. There's only a certain number of failures you can account for.
Yeah, g'day. I'm just wondering, with you mentioned the Faucet allows you to use non-vendor specific devices. With your Faucet switch, can I ask what kind of device that was? Was it a vendor device, or was it, what kind of equipment?
So if I go back, so all of this, so we've done I guess hybrid deployments where some of it's in software, some of it's in hardware. But for this deployment, we did everything in hardware, so there wasn't any software switching or anything. So the devices on the screen there are the ones we used. So there were 2 different models from Cisco, 2 different models from LA Telesys, and 2 different models from NovaFlow, all with different port counts. And some were running NPUs, some were running ASICs, some P4 ASICs, some commodity ASICs. So we kind of had one of everything, pretty much.
Cool. Cheers.
Anybody else?
I just want to ask, what's the future of the Faucet? What other features are you going to kind of try to work on the next year? You mentioned you have L2, LL3, and what are the plans for the next thing? And also more before integrations, or what are you going to do?
Great question, and I could go on for hours here. So we always have a huge list of everything we want to do. We're obviously a small team, so we can't get everywhere we want. The things we're playing around with at the moment is doing a bunch of tunneling type things. So we just added a feature this week that we'll release next week. I'm calling it Faucet teleportation. So you can push down a policy that collects a certain type of packet, so you match on protocol and that kind of thing. So you could say match on DHCP. And then you can say, I want it to egress at this switch on this port, and it builds a tunnel. If you change the topology, that tunnel changes, so your traffic comes out where you want it to. So we'd like to do a lot of work in there to actually make it more usable and have some use cases. I was at LCA last week, and a lot of people were asking for PV lands, so I'll have a think about good ways to do that. We want to do... the current thing we're doing a lot of work on is 802.1x, so we've got an experimental version of that that's working okay at the moment, but we'd like to extend it a lot. So as I said at the end of the day, this is usually an enterprise campus controller. It's not usually for running big L2 backbones or big campus, big data center networks, but we thought we'd give it a go and see if it worked. So yeah, lots of more enterprise features and that kind of thing. And then I think you had another question, which was, what was the end question?
I actually forgot.
It was a funny one, that's why I wanted to answer it.
The P4 thing, yes, yeah, the integration.
I have a lot of thoughts on P4. I think it's not ready yet, but I would like to see someone make a version that is ready. But we're very happy controlling it with OpenFlow at the moment. P4 is a lot different to OpenFlow, and there needs to be a lot of work to catch up to where OpenFlow is today. So I can use OpenFlow right now on about 6 different vendor kit. I can use P4 on 1.
Okay, nobody else has got any more questions? We'll thank Brad. So that's afternoon tea. We're a couple of minutes early, but so you've got a slightly longer break, and we'll be back at 3:30.